Welcome to the sixth lecture on properties of triangles. In today's lecture, we will be covering another new topic and basically defining something which is known as the centroid of the triangle, and then we will also discuss what is meant by the x-central triangle of a triangle. So, if you recollect, so let us say this is a triangle ABC. And let us say that this is the perpendicular from the vertex A to the side BC, to the opposite side BC. And let BE be the perpendicular from the vertex B to the opposite side AC. Of course, these two perpendiculars intersect at some point O, which we call the ortho center. And we had also shown that if we connect C and O by a straight line, and if we extend this straight line further, then this line meets the side AB at a point F in such a manner that this line CF is perpendicular to AB. And this we had proven in the last lecture. So, it turns out that all these three perpendiculars are concurrent at this point O, which is called the ortho center of the triangle ABC. Of course, we then derived formulas for the distance between the ortho center and the vertices of the triangle, which is basically these three lengths. We also derived expressions for the length of these line segments OD, OE and OF. We also defined the Petal Triangle. So, if we join these points F, E and D, where these perpendiculars meet the opposite side. So, if we join these 3 points, then we get this triangle in blue, which is called the Petal Triangle of the triangle ABC. And if you recollect, we had derived expressions for the lengths of the sides and the angles of the Petal Triangle. To be precise, it is very easy to see that because this triangle BCE is a right angle triangle and this angle is C. So, it turns out that this angle will be pi by 2 minus C, and further, because this triangle BOD is also a right angle triangle, this particular angle will be equal to, so this particular angle will be C. In a similar manner, one can show that this will be B, this will be A. Further, the length of this BD is very easy to find out by just considering the right angle triangle ABD. So, this entire length AB is C and this angle is B, therefore, BD is C into cos B. So, we just have to apply the trigonometric ratio to this right angle triangle ABD. So, C times cos of B is BD. Similarly, we can show that this length is B cos C and this length is A cos B. So, we had shown all these in the last lecture. And if we now focus on this triangle BFD, so if you look at this triangle BFD, then it is not very hard to show that because we already know that the value of this angle is, of course, this entire angle is B, and we know the two sides of this triangle BFD, and therefore, we can calculate the length of this remaining side FD by using the cosine law. FD is equal to B into cos B, and from there, because the if you look at this triangle BFD, then we see that all the sides, so for example, this side is A times cos B, this side is B times cos B, and this side is C times cos B. So essentially this triangle is similar to the triangle ABC because we are just multiplying all the sides by cos B everywhere. And from there it is then clear that this angle has to be equal to C, and this angle is A. And because this angle is C, so this particular angle then, so this angle then, which is angle CFD, so angle CFD will be equal to 90 degrees minus C. So pi by 2 minus C. And similarly, one can also show that this other angle is also equal to pi by 2 minus C, and therefore this entire angle EFD of the petal triangle, so the angle EFD of the petal triangle will be equal to pi by 2 minus C times 2, which is pi minus 2C. One can similarly show that also, in addition to this thing, of course, because this angle pi by 2 minus C is equal to the other angle here, and both of these angles sum up to the entire angle EFD, it turns out that the line segment FC is an angular bisector of the angle EFD of the petal triangle. Similarly, one can even show that the line segment EB is the angular bisector of and so is this line segment AD for this angle. And all these angular bisectors are meeting at this point O, and hence it follows that this point O must be the in-center of the petal triangle. So essentially what we have shown is that the ortho center of a triangle ABC is the in-center of the corresponding petal triangle of the triangle ABC. And of course, from all this analysis, we had shown that the angles, so the three angles are, so this angle is pi minus 2C, and then this angle is pi minus 2B, and this angle can be shown to be pi minus 2A. And similarly, the sides, we had already found out the length of this side FD to be equal to B cos B. This other side DE will be equal to C cos C, and this side FE will have a length of A cos A. So we had shown that for the petal triangle, we had shown that the angles are pi minus 2C, pi minus 2B, pi minus 2A, and the lengths are B cos B, A cos A, and C cos C. And then once we know all the sides and the angles, it was very easy to compute the expressions for the area. So we had shown that the area of the petal triangle, which we had denoted by delta prime, is equal to r square upon 2 times sine 2A, sine 2B, sine 2C, where this r is the circumradius of the triangle ABC. Further, we had shown that the circumradius of the petal triangle is half of the circumradius of the triangle ABC. This also we had shown. And what remained to be shown or derived was the expression for the in radius of the petal triangle. So the in radius of the petal triangle is given by r prime. So the in radius is equal to, we know that if we go back to our previous lectures, we know that for any triangle ABC, the in radius is equal to 4 times the circumradius times sine of a by 2 into sine of b by 2 into sine of c by 2. So, product of the sine of the half angles times 4 times the circumradius. So, applying the same formula to the petal triangle, we get the expression for the in radius of the petal triangle to be 4 times r prime times sine of. So, let us say the first angle is pi minus 2a and half of that angle times sine of pi minus 2b, again half of that angle, times sine of pi minus 2c half over 2. So, sine of pi minus 2c over 2. But r prime is r over 2. So, we use that, we get 4 r prime to be equal to 2 r, and this of course becomes cos of a cos of b into cos of c. So, the in radius of the petal triangle is twice the circumradius of the triangle ABC times the product of the cosine of the angles of the triangle ABC. So, that finishes the recap on the discussion on the ortho center of a triangle ABC. So, today we are going to discuss something that is known as the centroid of a triangle. So, let us say that this is our triangle ABC, and let us say that the point D is the midpoint of the side BC, the point and the point E is the midpoint of the side AC. And let us connect this midpoint to the opposite vertex of the triangle with a straight line. So, these two straight lines are called medians. Now, let us say that the center of the third side AB is F, or the midpoint of the third side AB is F, such that these two segments are equal in length. So, first of all, we will show that if we connect this C to the point of intersection of these two medians, which we denote by G. So, let us connect it like this. Then we will prove that if we extend this line segment CG further like this, then this line CG, when extended further, will intersect the opposite side AB at exactly the midpoint of the side AB, which is at point F. So, this we are going to prove, but what it essentially means is that since the CG intersects at the midpoint of AB, CF is also a median of the triangle ABC, and hence this shows that all the three medians CF, AD and BE are going to intersect at a common point G, which is called the centroid, and these line segments AD, BE and CF are called the medians. They are called the medians of the triangle ABC. So, we will now prove this fact that if we extend this line CG further, then it exactly meets the opposite side AB at its midpoint, which is essentially proving that all the three medians intersect at this common point G. But before we do that, there is another interesting property that is immediately clear if we observe this for a little while. So, let us connect this point D to E, and then if we look at these two triangles GED, and the other triangle is AGB. So, we will show that these two triangles are similar, but before that let us in order to show that, we need to first consider the triangles CED and triangle ABC. Now, if you look at these two triangles, what we see is that they have a common angle, which is this angle C, and further we see that the ratio of CE, the ratio of the side CE of triangle CED divided by the side AC of triangle ABC. So, this divided by this is equal to CD of triangle CED divided by BC of triangle ABC, and both these ratios are equal to half, and plus they have a common angle. So, what that shows is that these two triangles are similar, and therefore, this is nothing but equal to angle A and this is angle B, and therefore, this line segment ED is parallel to the side AB. So, now once we have shown that these two line segments are parallel, it obviously follows that this angle and this angle are equal, and similarly this angle here and this angle here have to be equal because these two lines are parallel, and of course, this and this angle are also equal because they are opposite angles, and that basically shows that triangle ABG is similar to triangle EGD. So, these two triangles, for these two triangles, the three angles are exactly the same, and therefore, these two triangles are similar, and from there it follows that GE, the ratio of GE to BG is equal to the ratio of GD to AG is equal to the ratio of DE over AB. However, just now we had shown that the triangle CED and the triangle ABC are similar. So, these two ratios should be equal to the ratio of the side ED of triangle CED over the side AB of the triangle ABC. So, because of the similarity of these two triangles, it follows that this ratio ED by AB is half, but that ratio is the same as this ratio, and hence this ratio is equal to half. And because this ratio is equal to these two other ratios, it follows that GE is, so from here this implies that GE is equal to half of BG, and also that GD is equal to half of AG. So, geometrically that can be visualized as GE being half of BG. So, what it basically means is that this length BG is double that of GE, or in other words, because this is a straight line, this length GE is 1/3 of this median BE. So, that basically implies that GE is equal to the length of the median BE over 3, and similarly GD is equal to the length of the median AD over 3. Sometimes in books it is also said that the centroid G divides the median in the ratio 2:1. So, this is 2 and this is 1. Similarly, this is 2 and this is 1. So, we will now have to show that the three medians indeed intersect at this point G, which is the centroid. In order to show that is true, what we will do is that we will join C and G and we will extend that further to F, and then show that these two line segments are of equal length. These are the midpoints. So, point D is the midpoint of BC, point E is the midpoint of AC, and these are the two medians. So, these are the two medians, and of course, this length AE is B by 2, CE is also B by 2. Of course, this is A by 2 and this is A by 2, and then what we do is that we join this point G to the vertex C, and then also extend it further, and let us say that this line CG, when extended further, it meets the side AB at the point F, which is here, and let us say that this distance is x, then this of course has to be C minus x, because this entire length is C. So, now our objective is to show that this x is equal to C minus x. So, these two are equal. So, that will prove that CF, the straight line CF, is a median, and of course, it will also show that it passes through this point G, because we first connected C to G and then we extended that straight line further to meet the side AB at this point F. So, this entire angle is 180 degrees. So, this is 180 degrees because this is a straight line. So, let us denote this length GE by T. Then obviously, as we just saw now, this length BG has to be twice of this length. So, it is going to be 2T, and let us say that this angle is theta. Then naturally, this angle turns out to be C minus theta, because this entire angle is C, and if this angle is phi, then this other supplementary angle will be pi minus phi, and let this be alpha and pi minus alpha. So, now if we apply the sine law, so let us apply the sine law to the triangle AFC. So, we apply the sine law to the triangle AFC. So, this particular triangle, and there what we see is that x divided by the sine of the angle opposite to it. So, x upon sine theta equals b. So, this is b upon sine of the angle opposite to b, which is alpha. So, b upon sine alpha. So, this is our first equation. We then apply the same sine law to the triangle CEG. So, where is CEG? CEG. So, we are talking of this particular triangle CEG. So, in the triangle CEG, t divided by sine theta is equal to b by 2 over sine of phi. So, the sine law applied to this triangle. So, t over sine of the angle opposite to it, which is theta, must be equal to b by 2 divided by sine of the angle opposite to it, which is phi. So, that gives us the second equation. Again we repeat the application of sine law to triangle CFB. So, CFB. So, this triangle. So, if we apply the sine law, we see that C minus x over sine of C minus theta equals A over sine of pi minus alpha, sine of pi minus alpha, but sine of pi minus alpha is equal to sine of alpha. So, A over sine of alpha. This is our third equation. And lastly, let us also apply the sine law to the triangle CGB. So, CGB. So, we are talking of this triangle now. So, in triangle CGB, we have 2t over, so 2t over sine of C minus theta equals A over sine of pi minus phi. So, A over, now sine of pi minus phi is equal to sine of phi. So, this is the fourth equation. So, we now have four equations after we applied the sine law to these four different triangles. Now, if we see the equation 1 and equation 3, we see that we have sine alpha at both the places. So, from equation 1 we have sine alpha is equal to b sine theta over x, and then from equation 3 we have sine alpha equal to a into sine c minus theta over c minus x. So, this we get by combining equation 1 with equation 3, and let us say that is equation 5. Similarly, if we combine equation 2 and equation 4, we see that we have sine phi at both in both the equations. From equation 2 we get that sine of phi is equal to b into sine theta over 2t, and then from equation 4 we get sine phi to be equal to a into sine c minus theta over 2t. So, since 2t is common to both the denominators here in equation 6, it follows that b sine theta equals a into sine of c minus theta. So, this follows of course from equation 6, and when we use this result in equation 5, we end up getting that x is equal to c minus x, because these two numerators are equal, and therefore, because of the equality here, the denominators must also be equal. And this statement therefore proves that since x and c minus x are equal, it must be true that this point f is the midpoint of the side AB, and therefore, the straight line CF is also a median of the triangle ABC, which passes through this point G, which is the centroid of the triangle ABC. So far in this lecture we have shown that the three medians intersect at the common point, which is called the centroid of the triangle. So, we will now go ahead and derive some expressions for the lengths of these three medians and also the angle formed by these three medians with the three sides of the triangle ABC. So, let us say that this is our triangle ABC, and the midpoints are D, E, and of course F. So, So, this is the median AD, this is the median ABE. They intersect at the centroid G, and then we of course have the third median CF. So, of course, these lengths are C by 2, C by 2, B by 2, B by 2, because these points F, E and D are the midpoints of the three sides, A by 2 and A by 2. So, let us try to find the length of this centroid FC. So, we know that this length or this median FC is a part of the triangle CFB. So, we can visualize this triangle CFB. In the triangle CFB, we already know that this angle is B. Further, these two lengths are already known. So, the idea here is that in any triangle, if we know the value of the angle at a certain vertex, and if we also know the length of the sides which are common to that angle, then using the cosine law we can find the length of the side which is opposite to that angle, and that for that we use the cosine law. So, in the triangle CFB, if we use the cosine law with angle B, then we get cos of B is equal to A square plus C by 2 whole square minus FC whole square over 2 times A times C by 2. And a little bit of manipulation here will give us that FC square is equal to A square plus C square over 4 minus AC into cos of B. Now, from the cosine law when applied to the triangle ABC, so the cosine law when applied to the triangle ABC, we know that cos of B is equal to A square plus C square minus B square over 2AC, and if we use this expression here, then we finally end up getting that FC square is equal to 2A square plus 2B square minus C square over 4, or in other words, the length of the median FC is equal to the square root of 2A square plus 2B square minus C square over 2. In a similar manner, the lengths of the other three medians, the length of the other two medians AD and BE can also be calculated, and we leave that as an exercise for the students. So, next we are interested in deriving expressions for the angles formed by between this median FC and the three sides of the triangle ABC. So, of course, the angles formed between the median FC and this side is, let us say we denote that by theta, and let us say this angle is beta, and the angle between FC and the side AB of the triangle ABC, let us denote that by alpha. So, we will now try to derive expressions for these three angles. So, towards that, let us try to first find the value of theta. So, we know that theta is part of the triangle AFC, it belongs to the triangle AFC, and if we apply the sine law to this triangle AFC, then what we end up getting is that, so AF which is C by 2, so AF which is C by 2 over sine of the angle opposite to AF, which is theta. So, C by 2 over sine theta equals FC over sine of A. And from here one can easily see that sine theta is equal to C sine A over 2 FC, and then here we can use the expression of FC that we just derived now. So, finally what we get is that sine theta is C times sine A over square root of 2A square plus 2B square minus C square. So with that we have an expression for sine of theta, and then theta of course is sine inverse of this expression. And the next thing would be to find the expressions for beta and alpha, which we do it in the next slide. So, let us redraw the triangle again. So, A, B and C, the midpoints D, E and so these are the three midpoints. So, we have already calculated the value of theta in the previous slide. Let us now calculate the values of beta and alpha. So, for beta of course, let us first write down the lengths here. So, for beta of course, we look at the triangle CFB, and so if we apply the sine law to the triangle CFB, then what we get is that C by 2 over sine of beta. So, we are looking at this triangle now. So, C by 2 over sine beta is equal to FC over sine of B. And from there it obviously follows that sine of beta is equal to C into sine B by 2 FC, which simply is equal to C into sine B over square root of 2A square plus 2B square minus C square. And now it of course just remains to find the value of the angle alpha. So, alpha can also be found from the applying the sine law to the triangle AFC itself. So, in triangle AFC we see that B divided by sine alpha. So, B over sine of alpha is equal to FC over sine of A, and therefore, sine alpha is equal to B sine A over FC, which becomes equal to 2A square plus 2B square minus C square. So, we have derived the expressions for the length of this median FC, and also the expression for the angles formed between FC and the three sides of the triangle ABC, which are theta, beta and alpha. In a similar manner, we can also derive expressions for the lengths of the other medians and their corresponding angles with the three sides of the triangle ABC, but that of course is left as an exercise for the students. Associated to every triangle ABC, there is another triangle which is called the X central triangle of triangle ABC. And let us quickly see what this X central triangle is. So let us say that this is our triangle So, this is our triangle ABC. And then we know how to find the in-center of this triangle ABC. That is something which we have already discussed in the previous lecture. So, for the in-center, what we do is that we find the point of intersection of the angular bisectors. So, this is the angular bisector. So, this is the angular bisector of the angle B, and let us say that this is the angular bisector of the angle C. So, these two angular bisectors will be meeting at a common point I, which is called the in-center of the triangle ABC. We had also shown that if we connect this vertex A to the in-center I, then even this line AI will turn out to be an angular bisector of the angle A. So, that we had proven in one of the earlier lectures. If we extend these all the three sides further. So, let us say we extend the side AB, the side AC, and then of course, if we consider the angular bisectors of these exterior angles. So, if we recollect, we had discussed drawing the angular bisectors of the exterior angles in the context of the ascribed circle. So, this point of intersection of these two external angles, which are opposite to the internal angle A, is called the point I1. And if we recollect, this point I1 was the center of the ascribed circle opposite to the vertex A. So, if we now if we look a little carefully, what we see is that this particular angle of course is B by 2, and this entire angle, because this angle is B, this entire angle has to be pi minus B, and because this green dotted line is an angular bisector of this external angle, this half angle here will be pi minus B over 2, and what that then implies is that this angle I B I1 will be equal to B by 2 plus pi minus B by 2, which happens to be 90 degrees. So, angle I B I1 will be equal to 90 degrees. So, which is basically this angle. So, this is 90 degrees. So, similarly, it is also easy to show that this angle will also be 90 degrees, and this of course is the, so this line is the angular bisector of the angle A, and it also meets the other angular bisectors at this point I. In a similar manner, we can also, just as we did for the ascribed circle opposite to angle A, we can also construct the ascribed circle opposite to this angle C. So, for that we just have to extend this side CB further and also the side CA further, and then just like what we did here, we have to consider these two angles, and we will have to make the angular bisector. So, let us say that this blue dotted line is the angular bisector of this external angle, and the angular bisector of this other external angle is let us say this particular blue dotted line, and they of course are going to meet at another point I 2, which is going to be the center of the ascribed circle opposite to the vertex C. And just as we had shown for I 1, we can also show that, because if we see here, this angle is b by 2 and this angle is also pi minus b, and therefore, this angle is pi minus b over 2, and from there it again follows that the angle I b I 2. So, I b I 2 is also equal to 90 degrees. So, we have shown that I b I 1 is 90 degrees and I b I 2 is also 90 degrees, and therefore, this entire angle I 2 b I 1 is 180 degrees, which implies that I 2 b I 1 is a straight line. So, this green dotted line followed this blue dotted line followed by the green dotted line is indeed the straight line joining I 2 and I 1, which also passes through this point, this vertex B of the triangle ABC. So, similarly, we can also construct the ascribed circle which is opposite to this vertex B. So, for that we just have to extend this side CB on the other side like this, and the side AB like this, and we have to consider these two external angles, and then we have to draw the angular bisectors of these two external angles. So, I am drawing that with this red dotted line. So, these two red dotted lines are the angular bisectors of these two external angles, and they of course meet at a point I 3, and this I 3 is the center of the ascribed circle opposite to the vertex B of the triangle ABC. And just as we had shown that I 2 I 1 is a straight line, in a similar manner it is very easy to show that I 2 I 3 is also a straight line which passes through the vertex A. Similarly, I 3 I 1 is also a straight line because both these angles are 90 degrees. Similarly, here also we can prove that these two angles are 90 degrees. The proof is entirely similar to the proof for that we just did now for showing that I 1 I 2 is a straight line passing through this vertex B. So, now that we have shown that all these three line segments I 1 I 2 I 3 and I 3 I 1 are straight lines passing through the vertices B, A and C of the triangle ABC. So, therefore, it follows that I 1 I 2 I 3 is a triangle, because we have three straight lines intersecting at I 1 I 2 and I 3, and this particular triangle I 1 I 2 I 3 is called the X central triangle of the triangle ABC. So, I 1 I 2 I 3 is the X central triangle of triangle ABC. So, our interest now will be to find the lengths of the sides of this X central triangle, and also the measures of the three angles of this X central triangle. So, the angles are not particularly difficult, because if we see here we had shown that this is pi minus b over 2, and similarly, because this entire angle here is pi minus c, this angle would be pi minus c over 2, and then because b I 1 c is a triangle, this angle is equal to pi by 2 minus a by 2. So, we have found the measure of the angle I 2 I 1 I 3 of the X central triangle to be equal to pi by 2 minus a by 2. And in a similar manner, we can show that this second angle of the x central triangle is pi by 2 minus c by 2, and this third angle is pi by 2 minus b over 2. And then for the we would like to now find the measure of the sides of the this x central triangle of triangle ABC. So, for that we will have to again use the sine law. So, if we apply the sine law to the triangle, let us first start with finding the length of the side I1 I2, but I1 I2 is a straight line which is equal, whose length is equal to I1B plus BI2. So, let us first find the length BI1. Now, if we apply the sine law to the triangle BCI1, if we apply the sine law to the triangle BCI1, then what we see is that BI1 over, so BI1 over sine of this angle, but this angle is pi by 2 minus c by 2. So, sine of pi by 2 minus c by 2 will be cos c by 2, cos c by 2 equals A over sine of this angle, and sine of this angle is cos A by 2. And this then implies that BI1 is nothing but equal to A cos C over 2 over cos of A over 2. So, this is the expression for the length of BI1, and then we are interested in finding the length BI2. So, for that let us apply the sine law to the triangle BI2A. So, if we apply the sine law to the triangle BI2A, we end up getting that BI2 over, so BI2 over sine of the opposite angle, which is this angle, and this so BI2 over sine of this angle. Now, this angle is not very difficult to find out, because we already know that this angle is pi minus b over 2, this is pi minus c over 2, and therefore, this angle is pi minus a over 2, because the sum of all the three angles has to sum to 180 degrees. And therefore, BI2 divided by sine of pi minus a by 2, which is cos of a by 2. So, BI2 over cos of a by 2 equals this length c divided by sine of this angle, which is cos of c by 2, and from there it follows that BI2 is equal to c into cos a by 2 over cos c by 2. So, now to find the expression for the length I1 I2, we just need to add these two expressions, and therefore, I1 I2 is equal to BI1 plus BI2, which is equal to A cos C over 2 over cos of A over 2 plus C cos A over 2 into cos of C over 2. Now, from the applying the sine law to the triangle ABC, we know that A by sine A is equal to C by sine C. So, this is already known to us, and of course, from here it will follow that C is equal to A sine C over sine A. So, let us replace this C by this expression. So, we end up getting that I1 I2 is equal to A cos C over 2 over cos A over 2 plus, so instead of C we use this expression, which is A sine C over sine A into cos A by 2 by cos C by 2. But we know that sine A is 2 sine A by 2 cos A by 2. So, that the cos A by 2 will cancel with this expression here, and similarly we know that sin c is 2 sin c by 2 cos c by 2. So, the cos c by 2 gets cancelled with the cos c by 2 here in the denominator, and what we end up getting is, so this first term remains the same and the second term becomes a sin c by 2 over sin a by 2, which is equal to, a is common, times sin a by 2 into cos c by 2 plus sin c by 2 into cos a by 2 over sin a by 2 into cos a by 2. But this expression here in the numerator is nothing but of the type, it is of the type sin a cos b plus cos a sin b, and therefore, that is equal to a times sin of a plus c over 2 by sin a by 2 into cos a by 2. So, taking it over to the next slide, we have I1 I2 equal to a into sin over sin a by 2 into cos a by 2, but this is equal to a into sin of pi by 2 minus b by 2, which is equal to a into cos b by 2 over, so we multiply both the numerator by 2 times and the denominator becomes 2 sin a by 2 into cos a by 2, but this is sin of a. So, what we have is 2 a upon sin a times cos of b by 2, but we know that for the triangle ABC, we know that the radius of the circumcircle, which is the circumradius, is equal to a upon 2 sin a, and therefore, using this here we finally get that I1 I2 is equal to 4 times r times cos of b by 2. So, what we have shown is that this length is equal to 4 times r times cos b by 2. In a similar manner, one can also prove that I2 I3 is equal to 4 times r times cos a by 2 and I1 I3 is equal to 4 times r times cos c by 2. So, with that we finish this lecture. So far we have defined what is meant by the x central triangle of a triangle ABC. We also derived the measures of the 3 angles and also the expressions for the lengths of the 3 sides of this x central triangle. So, from the next class onwards, we will start solving some problems. So, from the next lecture onwards, we will solve some problems on what we have covered in the last few lectures. Thank you.